Hello everyone, I am Akanksha Jain, Assistant Professor in School of Biosciences, IMS Ghaziabad. Today I am going to discuss the topic of material processing by physical vapor deposition. Basically, we require thin films coating on surfaces, so that the basic requirement for those thin films that is that they should be uniform throughout the wafer. There should be a good control. And in case we are doing coating on some curved surfaces like vials, then the sidewall coverage should be good. The material should adhere to the wafer well and should not peel off. The dust particles, they should not fall onto the wafer during the deposition process. The crystal structure of the film deposited should be of very good quality, and it should maintain the properties of the film. If we are depositing the alloys, then the composition must be uniform throughout the process. In PVD, that is physical vapor deposition, it is used to deposit titanium, titanium nitrate, tantalum, tantalum nitrate, aluminum, and a very thin film of copper, which is called a seed layer. Now, if the material is taken in solid state but sent as very small particles or atoms, and these are deposited on the wafer without any reaction. So such type of process in which the particles are depositing without any kind of reaction, this process is known as physical vapor deposition. Apart from this process, there are many other processes, for example, chemical vapor deposition, plasma enhanced chemical vapor deposition, and many more. Now coming to the setup of physical vapor deposition, the equipment is approximately 4 feet in height and 4 feet in diameter, and the material to be deposited will be on the top. As you can see from this figure below, the material to be deposited is aluminum or titanium, which is on the top. The tungsten will be in the form of a disc. This is in the form of a disc which is 1 inch in thickness or 5 to 6 inch in diameter. At the bottom, the silicon wafer will be kept on which the deposition will take place. Gases are allowed into the chamber and the chamber is evacuated with vacuum pump. Electrical connections will be giving the very high voltage. The negative plate will be near the tungsten and the positive plate will be near the wafer. So the tungsten iridium material, this is called this can be, of course, they can be aluminum, it can be titanium, or it can be tungsten. It is known as the target material, and it is the place, the silicon wafer is the place on which the deposition will be taking place. Now the air in the chamber must be removed and the vacuum must be created. The argon gas is sent inside and a low pressure is maintained. If we apply a very high voltage to the plates, a plasma will be generated. The plasma will have electrons and positive argon ions. Now the plasma cannot be generated by normal 230 volts. So the voltage has to be very high. Now these charged argon ions of gas will strike the negative plate and they will move towards negative plate since they are positively charged or some are uncharged, and they will hit the target with very high force. Now the argon ions, when they impinge on the target with very large force, the target atom breaks and comes out, and the number of target atoms that are released are known as spurting yield. Now it also depends on the speed of the argon ion, the angle of the impact, and also on the bond strength of the target. Tungsten is one of the very hard material. If a relatively soft material such as copper is used, the yield will be higher. Now the atoms from the target will come down towards the wafer with some force. Not all of them will deposit. Some of them will deposit, some of them will bounce back. And some may even bounce back and remove some of the materials already deposited on the wafer. It is similar to there's a hut where made of straw or something which has dust particles, and when you hit a ball on the roof of that hut, the dust particles will fall down and will cover the floor. So similarly here also the argon ions, they have impinge on the target. That would be any material that of which you need the deposition, and that target material will finally deposit onto the silicon wafer. So among the tungsten atoms that fall on the wafer, the fraction that stick to the wafer is known as the sticking coefficient. If all the atoms stick, then the sticking coefficient is 1. If none of them stick, the sticking coefficient is 0. And usually it is 0.7 to 0.8. The benefits of this physical vapor deposition is it's done in compared to the vacuum evaporation is the deposit of wide variety of metals and insulators can be done as well as of mixtures. The replication of the target composition in the deposited film is good, and the capability for in situ cleaning of the substrate prior to the film deposition can be done. So a self-sustained low discharge which is created by the breakdown of heavy inert gas such as argon. Alloy content of a multi-component target is replicated in the source film even if it consists material with widely different sputter yield, and this cannot be easily obtained. All this cannot be easily obtained by evaporation, because in case of evaporation, in case of alloy, since it's a multi-component, so depositions are not equal. This is all about physical vapor deposition. Thank you.